Hello everyone. In this lecture video, I will discuss an important concept called coefficient of correlation. First, we understand what is correlation. So, in multivariable distributions, we are merely interested in finding a relationship between two variables quantitatively. So, that concept, that measure is called the coefficient of correlation. What is correlation? Correlation is very easy to understand between two variables. So, if the change in one variable affects a change in another variable, then we say variables are correlated. There are two types of correlation. One is positive, another one is negative. So let us understand here what are the positive and what is the negative correlation. So if I have two variable here, x and y, so if there is an increase in variable x and there is also an increase in variable y, then we say that it is a positive kind of correlation. And similarly, if there is a decrease in variable x and corresponding decrease also in variable y, we say that it is also a positive correlation. That means when the variables are proportionate positively, we call it positive correlation. Or you can say if variables are aligned in same direction, then we say that those variables have positive correlation. Reversely, what is negative correlation? If there is an increase in variable x and there is corresponding decrease in variable y, then we say that it is a negative correlation. Okay, or if there is a decrease in variable x but there is a corresponding increase in variable y, then it is also a negative type of correlation. So we understand these correlation mathematically, quantitatively, how much correlation is there between the variable. So here are some examples where you can see uh, or you can observe the type of correlation. Suppose there is an advertisement and sales. So if advertisement I say X and sales I said Y in numbers, so what you are expecting by making more advertisement, sale will more or less. So in general scenario, if you have more advertisement, definitely sales should upgrade. So it has positive correlation. Similarly, price and demand of product. So whenever we say price of certain product is increased, demand automatically decrease. So it has a negative correlation. This one, first one have positive correlation, second one has negative. Similarly, income and expenditure. So whenever you have more income, your expenditures are increased. For example, students are getting pocket money. Once they will get into job, they will expenditure automatically increase. So this is a direct kind of positive correlation. Similarly, competition and sales in commodity. So whenever we have more competition, sale will less because number of peoples in the community are same. So if there are more shops in a particular community, sales of individual will decrease. So whenever competition will increase, sales will decrease. So this correlation is a quantitative measure of relationship between two variables, and we need to interpret them in terms of what variable x and y are representing. So let us see uh, how to represent the correlation between two variables in a type of diagram or pictorial representation which we call scatter diagram. So is what is scatter diagram? It is basically a representation of the variables x and y in xy coordinates. X variable is here, y variable is on y-axis. So we are aligning or we are pointing out these variables values in this xy plane, and we are seeing that whether these points are making any kind of pattern or not. So this type of plot is called scatter plot, and it's very important to analyze the relation between two variables. So let us see some particular diagrams which are representing here the correlation. So whenever you have points are very dense, this implies a good correlation, and if points are scattered randomly, poor correlation is expected. So let us see here some diagrams here. So now see here, this variable is x side and this is y variable, and these 5 points are indicated here, and they all lying in this line. Okay, so that means they are perfectly fitted along a line y equal to x. So this is called a perfect kind of correlation. And because they are aligned positively, so it is called a positive correlation. You can see here when I increase x, y automatically, y also increasing. Okay, so it's a kind of positive correlation. Whereas in this figure, you see the same points are indicating, but they are fitting as a negative correlation. When we increase here x value, y value started decreasing, okay, towards 0. And if it is nearby, x is nearby 0, y is at highest. So this is kind of negative correlation. And here we have positive correlation. Now see this third diagram here. This is not a perfect correlation, but it's very strong because maximum points are lying around this line y equal to x. So whenever points are scattered, so these points are aligned along a line y equal to x, we are expecting a high degree of correlation. I will later tell you what are the values for high degree of correlation and for perfect correlation. Now see this next diagram. So here we have a high degree of negative correlation. And now see here, this is the line y equal to x. That means when x is increasing, y also increases in same ratio. Now, but points are not clustered around this line. Okay, so here low correlation is expected. Similarly here in this next diagram, this is negative kind of correlation. They are following a pattern where we can draw a line that follows negative correlation between x and y, and points are also not clustered around this line, so low degree of negative correlation is there. Okay, so I hope you understand by drawing these points, and these cross directly plus signs are x comma y points. Each plus sign is denoting x comma y points. So next, it's very obvious here. You can see here in this one, there is no particular type of relation is observed because, and similarly for the second one also, there is no pattern the points are following. So in this case, there are no correlation. But remember that no correlation means here only it's a linear correlation. There is no linear kind of correlation. Okay, because the coefficient of correlation that is given by Carl Pearson, a famous mathematician and statistician, has given this kind of formula for computing a linear correlation between two variables. Okay, that is called the coefficient of correlation. Okay, so it's a mathematical measure of linear correlation. Okay, remember the word linear correlation. And it is defined as covariance of x and y divided by standard deviation. Actually, root of variance is standard deviation. So standard deviation of x and standard deviation of y variable. Okay, so this is denoted by r, or sometimes in some textbook it is denoted by rho x comma y. So we generally write r equal to or rho equal to and hiding these x and y variables, but it is understood that this r is the correlation between variable x and y. So we will see how to compute this r by computing this covariance between x and y, and by computing variance of x and variance of y. So in general, for the given data points, this covariance and variance of x, variance of y computation is not easy for larger data. So we have simplified these two definitions in some suitable form, so that by computing certain columns, we can compute this R between x and y. I will come to this point later. Before this, I will see some properties of this correlation coefficient R. So here, it is important to note that the correlation coefficient cannot exceed from -1 to 1. So lower limit is -1, upper limit is 1. R is lying between -1 to 1. That means mod of R cannot be more than 1. Should be less than or equal to 1. So R can be 0 and R can be 1. So if R is 1, we say perfect and positive correlation. So sign denotes the positivity, negativity of correlation, whether positive or negative, whereas the strength, if R is nearby 1 or -1, it shows strong correlation. And if R is, let's say, 0.5, it is a mild correlation. And similarly, if R is near about 0, it is showing very weak kind of correlation between x and y. So remember, the sign of this R is, let's say R is here 0, that means no linear, and here it is 1 plus 1, and this side -1. So whenever correlation is in this range, it's negative. And whenever correlation R is lying in this range, it is positive. Okay, and strength depend on how much it is approaching towards +1 or towards -1. It shows the strength. Okay, so R equal to -1 is perfect because it is exactly -1, and negative because of this negative sign. And if R is 0, there is no linear correlation. Remember that, no linear correlation. And if R equal to 0.5, it is moderate or mild. Okay, and if R is equal to, let's say, 0.10, it's almost very weak or low correlation. So by seeing this R value, we can say whether it is positive or negative. So we have a positive and negative correlation. And by looking at the number, how much it is close to +1 or -1, we can see the strength, positive or strong. And if it is R is going nearby 0, we have weak. And if R is 0.5 around, whether it is plus or it is minus, it's a average or moderate or mild correlation between x and y. Remember that if correlation is perfect, both variable increase or decrease in same proportion, as we see earlier in the diagrams, while in case of perfect negative, both will inversely proportional. And now here is very one of the important property. I have mentioned this particularly. So correlation of ax plus b and comma cy plus d equal to ac upon modulus of ac into r of xy. So what is there? I have variable x and y. So I will compute here r of xy. Okay. And now if I define some new variable, let's say u equal to ax plus b and v equal to c y plus d. That means I am adding a number on x and multiplying with a, and v defined as cy plus d. So adding a d and multiplying this by c. So here I am doing scaling by c and by a and changing origin by b and d. So this comes out that if I have taken this as because this is AC divided by A and C, so R of XY equal to R of UV. That means this correlation coefficient is independent of change of origin, as well as independent on change of scale. I will use this particularly change of origin because whenever I have data x and y and these data are very large and that may take more time in computation, so I will reduce them into u and v, and then u and v are what? I will subtract some average kind of b from x data and average number from y data d. So these numbers x and y will reduce to smaller numbers u and v. So computation will be very easy for us and we can do it manually. Okay. And another property is two independent variables are uncorrelated. So if x and y are independent, this means they are uncorrelated. But if r and x comma y equal to 0, that means correlation is 0. I cannot say variables are uncorrelated. Reason, r is measuring only linear kind of correlation. There can be any other form of correlation, let's say quadratic or cubic. So this kind of results we need to keep in mind. That means if r of x comma y equal to 0, it does not imply that x and y are uncorrelated, because there can be quadratic or cubic kind of correlation. As an example, we can see here, if I have certain data, let us write here, and you can easily verify this. If I have data x and y, let us suppose I have here -3, -2, -1, 1, 2, 3. And y here is 9, 4, 1, 1, 4, 9. So for this particular data, if you compute here this r of xy by applying any kind of definition or the main definition, you are getting 0. So this means r is 0. That means no linear correlation between x and y. But you can see here what is relation between x and y by closely observing. Y number is the square of x. Okay. So y is equal to x square. This means variables are correlated quadratically. Okay. So R measures only linear correlation. So in many times this MCQ question, if R is equal to 0, then what kind of correlation you are observing? It's saying strong, no correlation, variables are uncorrelated. So many times student click on uncorrelated, but there is also an option that no linear correlation. So if R is 0, it means there is no linear correlation. You cannot say variables are uncorrelated. There can be quadratic, there can be cubic, there can be any other kind of correlation between x and y. So I hope you understand this point. Now let's come to the computation of coefficient of correlation. And here we have written a very simple formula just by hiding this n. So here if you see, this is sigma x minus x bar, y minus y bar, where x bar is the mean of x, that is summation of x data divided by number of data, and y bar equal to summation of yi divided by n, where I equal to 1 to n, I equal to 1 to n, n is total number of data points. So this is basically obtained by definition after some simplifications, that is removing n from numerator and denominator. So it's very straightforward. By definition you can derive it and you can try it yourself. Now let's see how computation will be done here. So if I have x variable, I have y variable here, what are the things we need to compute, or how many columns we need to compute? So first I will compute x bar, then I will compute y bar by using definition, that is mean of x, mean of y, and then I will compute this x minus x bar first, So x minus x bar, I will compute this next column. Then I will compute x minus x bar whole square because it is there. So this number I will compute. And then y minus y bar, I will compute. And then y minus y bar square, I will compute because this is for every data points. And then finally, this is computed now. So I will compute the product of this. This product of this means x minus x bar and y minus y bar product I will compute. So how many columns we are computing? You have to see here. First column, second, third, fourth, fifth. And these two are given data points. So fifth column, 5 columns we are computing. Okay, and then lastly, I will take sum of all these columns. So I will get summation of basically this column summation required, and this column summation required, and this column summation required. So I will get these all quantities on right side, whatever the required here, or to get R. Okay. So this is the one of the formula here you can apply for finding a correlation. Now let's see another formula, which is again the arrangement of the definition, and we are making it to make it simple. So here is n times r equal to n times summation of xy into summation x, and this is actually summation x and summation y separately, and then square root of n times summation x square minus summation x whole square, then into same bracket this n times summation y square minus summation y whole square. Now let us see how many columns here we need to compute to get this R. So again, I have x data given, y data given, and then I need how many columns to compute this. So first I need x square here so that I can take summation. So x square I want, then I want y square also. Okay, you see the formula and compute required quantities. And then I want summation xy, right? This xy I need, so x and y. Anything else we want? No. Okay. So here you see we are computing 1, 2, 3. We are computing here only 3 columns. Whereas in previous formula, you have seen we are computing 5 columns extra. Okay, apart from these two given data sets. So this one is the direct method and it is easy to compute. Okay, R. So I will recommend everyone to use this formula, and because this needs only 3 columns computation, so summation of x I can get from here, summation of y I can get from here, and summation of x square I can get here, summation of y square, and here summation of xy I can get it. Okay, so all these quantities, summation x separately from here, summation y separately from here, so all these quantities which are required to compute R are computed by adding 3 more columns. There is one more interesting and the same kind of formula, except I have used here this property that change R is independent of change of origin. So as I said here, I have X data, I have Y data. Now I don't want to work on this data because these data are larger numbers, not in the count, like say 10, 5, 8. These values of x and y are larger. So when I do squaring or I do product of squares, it will be, or square of this, it will be not easy. So what I will do, I will write here u as x minus some mid number in x numbers. Okay, some mid number, whatever you choose, that's your choice, as a assumed mean of x, and then v I will choose as y minus assumed mean of y. So this assumed mean you can choose by yourself. Everyone can choose differently. There is no straightforward way. Whatever you think it is a mid value, you can choose that and compute x minus ax and y minus ax. So these two are new variables. Now I will do u square, v square, and uv. And in previous formula, in place of x and y, I will use uv. So because this r of x comma y is equal to r of x minus a I can say and y minus b I can say, and equal to r of uv. Okay, where x minus a is u and y minus b is v. So this is because we are see that this change of origin has no effect on correlation. So r of xy equal to r of uv. So this property can be used in the exam when you have larger number x and y. Let us see one example here. So here I have taken the data like the wellness club wants to examine whether there is a relationship between number of hours members spend exercising per week, okay, and their average weekly distance run. So I also love running. So here are 10 given members data is there, how much exercise they are doing and how much distance they are traveling per week. Okay, or they are running per week. So X and Y values are given. Calculate the Pearson coefficient of correlation between weekly exercise hours and weekly distance run. Also interpret the results. What is the meaning of interpret the result? Interpret the result means once you get R, what it indicates. Okay, based on this particular 10 data, right? So whether it is positive or negative and how much strength is there, that depends on value of R. Okay. So I hope you understand these formulas. So you can apply any one of the formula, either this uh, reduced number formula or this direct method or this simple way. Okay. It looks simple as formula, but it not simple in calculation. Okay. Because it directly came by the definition. So I have written here simple way means by using definition, but it required 5 columns extra to compute, and also mean it is taking. So sometime mean comes in decimals because it's stored exact mean. Okay, summation of xi divided by n. So sometimes mean also come in decimals. Okay, not a pure number. So it will be creating problems in calculation. So I recommend everybody to use this particular formula. R of xy equal to n summation xy minus summation x into summation y, and then square root of this all. Okay. So let us see, and here is a problem and I have solved also here. So these calculation I have done already. So x is there, y is there, x square, y square, xy. Okay. So I have operated on original data. No reduce on number is done. Okay. So because this x series is in almost in unit digits and y series also in not larger. Okay. So I can easily compute what is x square, what is y square, and then xy. Okay, manually as well as by using KLC. So I have this got this summation x, summation y, summation x square, summation y square, and summation xy. All the requirements are there. Now I can use the formula here. So I can write now here r equal to here n equal to 10 because 10 data points are given. So this is n times summation xy minus summation x into summation y divide by, and this I can write as very simply n times summation x square minus summation x whole square. So this is in one bracket, and in other bracket n times summation y square minus summation of y whole square. So it's easy to remember also. These terms corresponds to uh, standard deviation variance of y, and this term correspond to variance of y, and this correspond to variance of x, and this comes from covariance of x and y. So by using this we can put the values, and values are given here. So I can write now 10 into this xy is given as 1227 and minus 78 times this summation x, summation y is 152. So this is numerator. Now in denominator I will write here again. So 10 times summation x square, and that means 636, and minus summation x, this is 78. So 78 square. So it is in one bracket in other bracket some 10 times summation y square, which is 2 3, how much it is, 2374, and minus summation y whole square, and that means 152. Okay, 152 whole square. So definitely this computation you have to do in calci. It cannot be done manually. Okay. So after solving this, I will get 414 divided by square root of 276 and into 636. And finally, I will get r of x comma y around 0.9899. So I can see it is very nearby to 1 and its sign is positive. So we have a positive correlation. Okay. And because r is near to 1, it's very uh, positive and strong kind of correlation is there between x and y. And that means as number of hours per week is increased, the distance running distance also increases. Okay, so which is common. So this is the one problem, and second problem I have taken here, and this is particularly taken in mind that which formula you are going to use. So university wants to study whether there is relationship between the number of hours students are spending in studying per week and their performance in a weekly test out of 100. So data for 10 students are taken here, and you can see test scores are the number, and these are the number of hours per week studied. So what kind of correlation you can expect from this data? Okay. So here you see that X is okay, it's not big numbers, but Y numbers are very larger. Now I recommend everyone to solve this particular problem by directly computing in terms of X and Y. I have done here by reducing these numbers X and Y into smaller numbers. Okay. And it's very interesting to see by yourself, by verifying yourself, how much time it is taking when you are taking directly X and Y, and when you are it is doing by reducing the numbers. So here is the table given, reduced table. So what I have taken here from the data, you can see 10, 14, 12, 18, 20, 16, 22, and these are the numbers. I have taken here 16 as a assumed mean. Assumed means it is not sure. Just you assume for your convenience. You can take 20 also. You can take 18 also. You can take 15 also. Okay. Whatever number you will take, it will not change the final answer. Okay. Because R is independent of change of origin. So I have taken here 16 in the X series and the 64 in Y series as assumed mean. So next I will do here, I will compute U and V. Okay, by subtracting the 16 to all X number and by subtracting 64 from this Y numbers. Okay, so these are my new numbers on which I need to compute the correlation. Okay, these are forgotten. Okay, now U square, V square and UV, and then summation of all these columns. So summation U is 3, summation V is 10, and it's very interesting. You can see your data was earlier in 10, 12, 15, 20, 22, and Y was 52, 62, 70, 65. Okay, now U and V are the numbers. They are changed into single digit. So it's very easy manually to do square and the product. Okay. So this can be done without calci. So those who forget the calci or they are not want to use, they can change this number. So here is the solution of this particular problem. So we have constructed the table here. So what is the UV? UV given, okay, it is hidden here. It is 156, a small number. Okay. Now by using the formula, I can easily compute what is this R. So R of U comma V equal to, I will write n times summation UV minus summation U and summation V divide by square root of this n into summation U square minus summation U whole square in one bracket, and other bracket n times summation V square minus summation V whole square. So this can be easily computed, and it is, the numbers are now here 10 times 156, which is UV, minus it is 3 into 0 and divide by square root of 10 into summation U square, which is 123, minus summation U means 3 square in one bracket. In other bracket I have 10 times into 258 minus V square means 0 square. So this is easy calculation, and this is now comes as R is approximately 0.88. So this is actually R between X and Y, and which is R between U and V. So this is your final answer. You can write the property that R of X minus A comma Y minus B equal to R of X comma Y. So this is the property I am using here, and this is this number is called U, this number is called V. So I hope you understand this concept of correlation and coefficient of correlation calculation. Now here I am leaving a problem to you, and you can see here the height of father in inches and height of his son is given for 10 members, not the 10 member, how many you can count. So these numbers are larger, okay, not in the count, okay. So you can check which formula you want to use, and I have mentioned here a table. For the reduced table, you can see here I have taken here AX as 68, AY as 69. You can choose any other number and do this, fill this data in the table. I have important here, whatever UV you will choose, you will get same here. This same answer actually. Based on this, you will get these summations 36, 44 and 24, and these two are 0. It's very interesting. So calculation is very easy, and R is around 0.63. So this implies R equal to 0.603. So this implies moderate kind of correlation is there between height of father and height of sons. Okay. So that means it does not necessary that if father height is uh, uh, more, then son height will also be more. Okay. That's why it is a moderate type of correlation. So this is all about on this coefficient of correlation topic. I hope you understand, and this is totally a problem solving approach. So thank you all. Thank you so much.